Okay, so it's that time of the year again. Final exams are coming in, and we are going to review once more the entire curriculum of science. And yeah, this is gonna be the last time. Here we go. Based on this, it's not really too long, but there is a lot of solving. I'll be real with you. That let's see what involves solving real quick. All right, that involves solving that one and that one. Okay, let's just get started with it. Okay, so first and foremost, let's start with the carbon atom. The carbon atom is atomic number 6 and has 4 valence electrons. So, to recap, valence electrons are basically the outermost electrons in a atom, and they are responsible for bonding. With 4 valence electrons, you can do up to 4 single bonds. You can do up to 4 single bonds with another atom, so that you can achieve the 8 required for stability. In contrast, we also have atomic number 6, which is also important. So in carbon atoms, we have two types of two types of bonds, two types of chemicals. So first we got the inorganic, that's carbon only. That's really just, for example, diamonds and graphite from pencils. That's one of the few examples there. But for organic, it gets really complex, and I will first go layer by layer to show that you shouldn't get overwhelmed. First and foremost, we got under organic, we got carbon-hydrogen bonds. And of course, we got first and foremost hydrocarbons. Hydrocarbons are made out of C and H only, as their name suggests. Carbon and hydrogen. When you draw these when you draw this how do I call this? When you draw this like something like this, it's, as you can see over here, it's H and C only. Next, we have alcohol. Alcohol is defined by OH attached to C. So if you see something like this, CO and then H, that's obviously an alcohol. It's usually in drinks and medicines, and of course it ends with OL and is polar to all substances. So polar, we got ending with OL, it's used in drinks and medicines, and we have an OH attached to C. Meanwhile, for esters, these are responsible for the sweet smells you see in fruits and are usually volatile. They're just characterized by the COOH over here, and then you got the O, and then you got R, something like this. That's what you're going to find, and R can be any element, as per usual. And yeah, as I said, sweet smells. Lastly, biomolecules. There's 4 types of these, and they're just 4 different types of molecules that you can see in a body or in life. We have all of these, and I'm gonna explain them later. So first and foremost, let's go under hydrocarbons, and let's go to alkanes. So alkanes is a single bonded CH. They're just purely made out of single bonded CH. Now, in the last test, I need you to please listen to this one. We need to memorize these, okay? We need to memorize these, okay? Let's make that clear to us. N is the amount of carbon, and hydrogen is proportional to that. So as you could see, we have an N and then a 2N plus 2 over here. So if we have 5 carbon, that means we have 2 times 5 plus 2 hydrogen, which is just 12. So that's how the bonding system works. So these are used in fuels, butane, etc. Yeah, that's really all you need to know of alkanes. And pay attention to these lines, as you could see over here. Those are the bonds, and remember, we can only have 4 of them per carbon. So 1, 2, 3, 4. And as you could see, we got 3 C's and 8 H's. So we have 3, and then 6 plus 2, which also follows our formula. So that's all you need to do about alkanes. Meanwhile, for alkenes, we have at least 1 double bond, and it's used in rubbers and plastic. The formula for this one is CnH2n, so just double the amount of hydrogen. Just double the amount of hydrogen from carbon. So if this is 5, this one is 10. Drawing it looks like something like this, and as you can see, we have 2 lines over here. one line over there, and another line over there. That's 4. So one line here, one line there, one line there. Two lines here, so that's also 4. Oh, I forgot to mention, but only alkanes are the saturated one. This means that this contains the most hydrogen. Meanwhile, for alkenes, yeah, these are, and alkynes, these are both unsaturated. Let's now move on to alkynes. Alkynes have at least one triple bond and are used in preservatives, and they follow these formula. So we got for 5 hydrogen, we have 5 carbon, we have 10 minus 2, which is just 5 times 2, that's 10, minus 2 hydrogen. So that means it's 8. So that's how we solve for the amount of carbon and hydrogen. So just pay attention to the alkanes, the alkenes, and alkynes. Those are the prefixes you want to look out for. So alkane, alkane, alkene, and alkyne. That's all you need to know. And the last one is aromatic. This is just used in medicines and has this little benzyne ring over there. That's all you need to know. It's very easy to distinguish. There's not really a fixed formula for it, so you just go about it. Once you see this, that's immediately an aromatic hydrocarbon. Okay, moving on to biomolecules. So first and foremost, we got carbohydrates, which are usually made out of CH and O, carbon, hydrogen, and oxygen. These are our main source of energy and are found in cells. Also, these are hydrophilic, which means they are semi-soluble in water. Well, it will eventually dissolves, and that's what differentiates it from the next one, lipids. Lipids are also made out of CHO, as you could see over here, but as you can see, it's non-polar, and water being polar means it's completely hydrophobic, which means it cannot mix with water no matter how hard we try. And this is also a long-term source of energy because when you're going through a weight loss transition, you'd usually use the carbohydrates first, and then once you haven't eaten in a while, the fats would start to burn, and that's what we call our lipids. Hence why these are called long-term energy sources. They aren't used until for long-term effects, such as prolonged without eating, like 3 days without eating, you'll probably use up some of your lipids by then. Meanwhile, for proteins, these are for muscles and nails usually, and are made out of C, H, O, and N, and they just simply support the immune system. Last but not the least, it's nucleic acid. These are made out of C, H, O, N, and P. That's carbon, hydrogen, oxygen, nitrogen, and phosphorus. Is it phosphorus? I forgot. But yeah, it's used in the synthesis of proteins in cells, and it carries your genes. And that's really it for the carbon atom. So there we go. Entire unit knocked down in one swoop and in one table as well. Very nice. Alright, so for mole concept, molar mass, molar conversion, and everything that, I'll need to reuse some of our slides, so let's have a little refresher, okay? So, before we begin with these word problems, I'm just going to talk about the thing about mole concept, okay? So, mole concept derives from this number by Avogadro. This is called Avogadro's number. It's this absurdly large number, but basically, to use this number, it's the amount of particles in 1 mole. And a mole is not really a fixed measurement because we have grams per mole. And basically, it could be 12 grams per mole or 300 grams per mole. It depends on the molar mass, which we'll solve for later. But basically, what it states is that you need 300 grams of this substance to match 1 mole or this amount of particles in that sample. So that's what we call the mole concept. It just revolves around this number. I don't think we really need this number, but it's good to know it. For our calculations, disclaimer, we will be using this periodic table that's been rounded off to the nearest 2 decimal places. Alright, so let's get started, shall we? I have already given some things that were corrupted, such as this one, so yeah. So let's read it. First problem. Ammonium iron 3 sulfate dodecahydrate is used in textile factories to guarantee that dyes stick to the clothes well. This helps fix the dyes onto the fibers with producing vibrant, long-lasting hues that don't fade readily. Determine its molar mass. So starting off fairly simple, but although this is most certainly one of the harder ones for molar mass. Let me just repair the damages here. Okay, there, much better. So, first and foremost, what are we required? The molar mass. Now, to find the molar mass, it's just, it's just element times coefficient. Each element. Now, let's break down this one step by step. First and foremost, let's start with the NH4 part. NH4. So this is this is just in the brackets, so we can just treat this as N and H times 4. Oh my gosh, my brush is ridiculous. Okay, let me just shrink it down, sorry. Anyway, N, okay, now let's do 10. There we go. Okay, so we got N times 1 and H times 4. So let's convert that first. So we go over here and we want to find nitrogen, which has a value of 14.01. We capture that, we copy that over here, 14.01, and we times that by how many? We don't have a coefficient, so just 1. Meanwhile, we do the same for hydrogen. So let's go back here. We have hydrogen over here, 1.01. So that's going to be 1.01 times 4. Let's now find the equivalent. So this is obviously 14.01. And this is plugging into our calculator. By the way, calculators are allowed on the exam. I forgot to mention that. So let's take our calculators. That's going to be 1.01 times 4. That's going to be equal to 4.04. And we're going to add these together. We have 14.01 plus 4.04. That's going to be equal for 18.05 for this particular example. Let's just take a look at our answer key so far, and we're doing good. We're doing good. Okay, so let's I'll keep explaining. Next one, we got an Fe in parentheses SO4 and close bracket 2. Let's focus on the Fe first. So the Fe is clearly a standalone because it's not next to any number or anything, so we can easily say just Fe times 1. But here's where it gets a little bit interesting and confusing. So once you see a coefficient here, you need to distribute it to each of the elements here in the brackets. So that's going to be 2 times 2 sulfurs. So 2 times 2, S times 2. And then 2 times 4 oxygens. 2 times 4 is 8. So oxygen times 8. Once again, let's quickly find our individual molar mass. Okay, iron is 55.85 times 1. And then we got sulfur. Sulfur, where is sulfur? There, sulfur, 32.07. So 32.07 over here for silicon times 2 because we have 2 of them. And lastly, oxygen over here, that's 16. So just 16 times 8. Then that's all added up. So we got 55.85. Plug it into the calculator. We got 32.07 times 2. That's going to be equal to 64.14. And lastly, 16 times 8. That's just equal to 128. And that is that is I think that's it. Yeah, that's it. So we can add it up now. 128 plus 64.14 plus 55.85, that's equal to 247.99. We're getting close. We just need to do the last part, which is 12H2O. For H2O and other, whenever this is it, this dot represents just add these sums together, not multiply. And H2O is usually just like bracketed, so just multiply hydrogen and oxygen as well. So you can write it like this: 12H2O, like this. Then 12 times 2 hydrogen is 24 hydrogen, because 2 times 12 is 24. That's equal to 1.01 times 24. And we also have 12 times 1 oxygen, that's 12 oxygen. That's equal to 16 times 12. And this is equal to 1.01 times 24, that's equal to 24.24. And then you got 16 times 12, that's equal to 192. Then we can add that up, 192 plus 24.24, that's equal to 216.24. Now that you got all those three values, we can at last solve for the molar mass. 18.05 plus 247.99 plus 216.24. That's equal to 482.28 grams per mole. And that's how we express our molar mass, grams per mole. Very nice, very nice. This is definitely one of the most complex ones. Let me just make sure with my, yep, that is correct. Okay, let's continue. Calculate the mass of 2.5 moles of sodium chloride to prepare a sodium chloride for an experiment. Okay, so this is the formula indeed. So we have given 2.5 moles mole of NaCl, and we given mass. We want mass of 2.5 mole NaCl. Now, to solve this one, we just need to use this formula. So we need to find the molar mass first of NaCl. There's no exponent, so we just find Na and Cl. Okay, Na is over here, and that's 22.99. Meanwhile, Cl is over here, that's 35.45. Therefore, we add these two together to get NaCl. So just add them together, 22.99 plus 35.45, that's equal to 58.44 grams per mole. And since we have 1 mole now, we can just multiply 2.5 times 58.44. So just do 2.5 times that one, and you get our final answer of 146.1. Only for this one, since we already have more than 1 mole, we just put grams. 146.1 grams. Let's just check our answer right there. Yep, that is correct. Okay, very nice. Next one. A jeweler is working with 15.8 grams of silver to create a custom ring. Now we're looking for the amount of moles. First and foremost, let's list our given. 15.8 G of silver. And then we're required moles of 15.8 G of silver. Now since we multiplied over here to find it, this time we're gonna divide. So since Ag is just an element, we have given over atomic mass. equals moles. Let's plug that in. It's very easy. So we got 15.8 over, what's Ag? It's over there, 107.87. 107.87. And then that's just equal to, let's put that in our calculator, 15.8 divided by 107.87. That's just going to be equal to 0.1464. And since we only consider the first two decimal places, it's approximately 0.15 moles of Ag, or silver. 0.15 moles of silver. Let's check our answer key once again. Very nice. Alright, I'll take a little break for this one. I'll eat dinner and then I'll be back to you with the percentage composition. Okay, so I'm back. Let's finally finish this fourth problem over here. Once again, alright, let's read the problem. You are preparing a solution for water treatment experiment to remove contaminants from the water by employing iron 3 sulfate hexahydrate. For the proper concentration, calculate the compound's molar mass and the percentage composition of each element in iron 3 sulfate hexahydrate. Oh, mouthful. But we can just repeat the same process here and we'll deploy a new strategy as well. So first we have the required molar mass of each compound, and I will explain to you how we can do this later. So first, let's start with the molar mass. So let's start with the Fe2. Let's divide it into three parts, shall we? No, two parts. So Fe2 in parentheses SO43. First and foremost, clearly there's two Fe's over here. So Fe times 2. Fe times 2. Next, we distribute this again. So S becomes S3. So S times 3. Then we get O times 4. O4 times 3. So that's just O12. Then let's calculate. First and foremost, let's find Fe over here. Fe is there, 55.85. And then next is S, sulfur. Sulfur is 32.07. Oh, sorry, Fe times 2. My bad. So 55.85 times 2, that's equal to 111.7. Then for S times 3, let's check out the 32.07. That's 32.07 times 3. That's equal to 96.21. And lastly, O times 12. So O is 16. So 16 times 12 is equal to 192. Next, 6H2O. Alright, 6H2O. We have 12 times hydrogen and 2 times, 6 times oxygen. So, hydrogen, we already know that that's 1.01 times 12. So that's going to be equal to 12.12. Meanwhile, 6 times O, so that's 16 times 6, that's equal to 96. Alright, so if we ever have any overlapping, so let's now start with the molar mass first. So the molar mass is going to be, let's put this in, 111.7 plus 96.21 plus 192 plus 12.12 plus 96. So we should get an answer of 508.03. Wait. Did I do something wrong here? Hold on. 6H2O times... It's just my horrible handwriting. Hold on. Just my horrible handwriting. Okay, I think this is correct. Yeah, that is just my horrible handwriting. Let me make sure. Oh, I made this wrong. So yeah, this was the correct answer. Huh, my bad. I was just a little confused. Anyway, this is the correct answer. Grams per mole. So we're gonna introduce a new formula. It's gonna be element over molar mass times 100. So I want you to list down all of the elements we have discovered so far. So that's Fe, S, O, and clearly we have H. And then you want to make a fraction out of them, all of them. Then at the denominator or bottom, just simply put the molar mass. So that's going to be 508.03, all at the bottom. So just like that. Now, just put the amount of the contributions of each element there. So for iron, we obviously got 101.7. For sulfur, we got 96.21. For oxygen, we have 192 plus 96 over there. So as you can see here and here, that's going to be 288. And lastly, hydrogen, we have 12.12. Then we just put each of these into our calculator. Make sure to times these by 100, by the way, all of it. So for the first one, we have 111.7 over 508.03. That's times 100. And after rounding off, we get about 21.99% for iron. For silicon, let's do that again. We have 96.21 over 508.03 times 100. We get about 18.94% S. For oxygen, let's try that again. We got the same thing over there, but we put on top 288 instead. Put it into the calculator and we get 56.69% of oxygen. And last but not the least, we have the hydrogen, which is 12.12 all over that. And that's just equal to about 2.39. So let's add all of these to go. 2.38, I think. Yeah, so we have to add all of these and make sure it's 100. So 21.99 plus 18.94 plus 56.69 plus 2.38. So if you get 100, so the acceptable answers are 100, 100.01, or 99.99. So these are all acceptable. But yeah, this is your final answer, and this is your molar mass. And that's it. That's the percentage of compound and the mole concept. Once again, another almost clean swoop for another unit. So let's go on to the next one, and it's even more calculations, unfortunately. Okay, so we're back at our usual, your usual, what do you call this? Our usual setup. So we have covered all the mole concepts and the percentage composition of a compound, and we're kind of halfway now, so yeah, we're now into the second unit. So this is going to be empirical and molecular formula. This is very short and very simple. Not really simple, it's pretty complex, but I'll try to make it simple. Okay, let's start. First and foremost, what is the empirical and molecular formula? So empirical is just, okay, just listen up here. Empirical's formula is just the simplified ratio of each element. So like 2 is to 3 is to 4. However, empirical shows the complete amount of atoms. So like 3 is to no, not 3. 6 is to 9 is to 12. So what we can say is empirical is the simplest ratio, while molecular is the exact ratio, the full ratio. And that's what we can say about each two. So, how do we do this? I'll give you 2 sample problems. First, I'll go in depth with the first one, and then the second one will go a little bit faster. Okay, first let's read the problem once more. A chemical intermediate used in the manufacturing plastics and is also used in pharmaceuticals has the following percentage of composition: 65.45% carbon, 5.45% hydrogen, and 29.10% oxygen. What is the empirical formula of the compound? Let's stop there first and start to find the empirical formula first. So for empirical formula, step 1. Percent to mass. So what is percent to mass? You see we're given these percentages over here. So let me just merge these real quick. Yep. So we have these percentages over here, right? Now I want you to just simply convert them to grams. So 65.45 grams of carbon, and then 5.45 grams of hydrogen, and 29.10 grams of oxygen. Perfect. That's as simple as that. Second, mass to moles. Okay, I just realized I'm missing the periodic table. Let me go grab it real quick. Alright, I have successfully got a copy of the periodic table. We don't really need this, so let's just put it over there. Okay, so we return to mass to moles. So to do this, basically just get our given over atomic mass for each of these elements. So we put 65.45 over, let's find the mass of carbon. Carbon's 12.01. Right, very nice. Next one for hydrogen, we have 5.45 over, we already know it's 1.01, right over there. Last but not the least, we got 29.10 over oxygen's mass. So let's just do C, H, and O. Let's keep everything aligned. And that is 16. Very nice. So once again, we want to find the moles. So just plug these values into your calculator, and we should be able to get our empirical and molecular formulas. So let me just find our reference paper to begin with. Okay. All right. Okay. I have my reference paper now. Let's start putting in our values. So we got 65.45 divided by 12.01. Oh, wait. 65.45 divided by 12.01. That's equal to about 5.45 mole of carbon. Next one. We got 5.45 divided by 1.01. That's equal to about 5.40 moles of hydrogen. And lastly, 29.10 divided by 16. That's equal to 1.82 moles of oxygen. That's approximately like that. So very good. We have now 2 steps. 3. divide by small. Now, you have these values over here. You want to pick out the smallest and divide all three of them by those. So since the smallest, so we can just copy this, 5.45, 5.40, and 1.82. So, oh, by the way, that's a fourth step. I'll explain later. Anyway, so divide by small. So we have 1.82 as the smallest, so therefore everything gets divided by 1.82. Very nice. So, let's put those first. 5.45 divided by 1.82, that's roughly equal to 3. Meanwhile, 5.40 divided by 1.82 is roughly 2.97. And obviously, this is just 1. Now, it's time to do our fourth step, which is multiply till whole. But there are some exemptions. So, first and foremost, you round every single number up. You don't do anything. You just round off every single number to its, well, nearest whole number, unless it's the following. 0.5 or 0.50 results in multiplying by 2. 0.33 results in multiplying by 3. And 0.25 results in multiplying by 4. These are the special cases. Otherwise, just keep it to rounding off to the nearest whole number. And in this case, we just have times 1, times 1, and times 1 because they're all whole. So that is C3, and that's H3, and that's just O. So the empirical formula is C3, H3, O. Very nice. Let's now go to the molecular formula. Now this is now the second part. As I said, there's 7 steps to this entire ordeal, and we've already covered 4, so there's 3 more. First and foremost, let's start with the molar mass of our empirical formula. C. So let's do 1. Find molar mass of empirical formula. That's EF. So that's C3, H3, and O. C times 3, H times 3, and O. So let's find out those values. C3 is just C, carbon, 12.1, 12.01 times 3. H, we all know it by now, is 1.01 times 3. And just O is just 16 times 1. Perfect. Now, we just need to, first and foremost, we need to find out the molar mass. So that's 36.03 plus 3.03 plus 16. Let's put these into our calculators. 36.03 plus 3.03 plus 16. That is equal to 55.06 grams per mole. Perfect. And now we just need to go to the given. Oh, sorry, 50, just put 55.06, sorry. And then we just have to add, okay? We just need to have the given. So this is step 2. Find multiplier. And that's equal to given over mm of EF. So our given is 110. So we put 110 over here, all over 55.06. And once again, this time we just round it off to the nearest number, which if you put into the calculator is just 2. And finally, 3, distribute. Write the empirical formula once more. Bracket it, and then add your multiplier over here, then solve. C3 times 2 is C6. H3 times 2 is H6. O times 2 is just O2. And that is your molecular formula. Very good. And there you have it. That is your complete guide to making the empirical and molecular formula. Let's just do one more problem, but at a slightly faster pace. Alright, step 1, percent to mass. 22.45 grams of Na, 30.25% grams of phosphorus, and 47.30 grams of oxygen. Next, mass to moles, 22.45 over, what do we have here for sodium, 22.99. Next, we have phosphorus. Phosphorus is over here, 30.97. So we got 30.25 over 30.97. And then 47.3 over 16. That's oxygen. Alright, time to divide once again. No rounding off yet other than the 2 decimal places. So 22.45 divided by 22.99. That's equal to about 0.98. Next is 30.25 divided by 30.97. That's equal to about 0.98 as well. Then we got 47.30 divided by 16. That's equal to about 2.96. Next, divide by small. So the smallest is clearly 0.98. So 0.98 divided by 0.98. Same thing for this one as well. And last one for oxygen, 2.96 divided by 0.98. Plugging in these two to the calculator obviously gives us 1. And 2.96 divided by 0.98 is roughly 3. Once again, since all of these are whole numbers, we just times it by 1. They're not any of these special cases. So we get a formula of NaPO3. Very good. Then let's continue. NaPO3, that's going to be Na, that's equal to 22.99. Phosphorus, which is just 30.97 as per given, as you could see over there. And O times 3 is just 48. Now let's add all of these up. 22.99 plus 30.97 plus 48, that's equal to 101.96. Then following the formula over here, we take the given of 305.90 over 101.96. Let's put that into our calculators. 305.90 divided by 101.96, that's equal to, well, basically 3, and then we just multiply. NaPO3 bracket 3, so that's 3 times Na, so that's just Na3, P times 3, that's P3, and O3 times 3 is just O9. And there you go, that's your molecular formula. And that's it. That's another unit down in one swoop. This is going surprisingly fast pace for an ETA guide. And yeah, it's literally still the same day, by the way, March 20th. So yeah. So first and foremost, this is gonna be a really sad one. But before we move on to the next topic, which is gas laws, I do have to just mark this already as read. Look, the kinetic molecular theory of gases is really, for me, the most confusing part of this. I just tried to understand what was going on, but it just seems like I can't apply the postulates properly. I can understand them, but only in a proficient level, and like I just don't have the amount of, I just don't have the confidence, and I don't think I have the skill to discuss this. So, but rest assured, this will be very like minimal. It's just gonna be like in the multiple choice and maybe just part of like a 1.2 point-ish essay. So you don't need to worry too much about that, and you can always review from the slides. But these 5 laws are the ones that are a real pain. And it's even more calculations. Oh my gosh, let's continue. Let's prepare our materials then. And you are watching possibly the last segment of the video and last of study guides for science. I hope you have, I hope this channel has helped, and let's get right into it. So, here we go. Gas formulas. So throughout this, what they call this discussion, I'm going to just tell you simultaneously when we're solving a problem, how is it related. First and foremost, let's divide our board into 5 segments over here like this, so that we have 5 segments to do each of the laws. All right, let's get started. So I'll mention some important stuff first. First and foremost, R in the ideal gas law is always 0.0821, and from Celsius to Kelvin, it's just add 273.15. So we need to make sure every single temperature is at Kelvin. Let's get started. First and foremost, I'm gonna go by the order of discussion here, so it's boils. So let's do number 7 first. So Boyle's law, by the way, you do not need to memorize these. These will be given, and I repeat, this will be given in the final exam. Will be given. But let's just write it. So we got Boyle's law that states that PV1 is equal to PV2. So P1, Boyle's law. PV1 is equal to P2V2. So the relationship pressure and volume, and these are inverse. As one goes up, the other one must go down. That's what Boyle's law is all about. As pressure and volume have an inverse relationship. Let's prove that right there. So we have 8 liters. A flexible balloon has a volume of 8 liters and a pressure of 2 atmospheres. Find the volume. If the pressure is increased to 4 atmospheres, what will be the new volume? Now, this is very simple, and it doesn't even need a calculator. Let's replace V2, the volume 2, with a variable such as, let's just say, x. So this is equal to 2 times 8 is equal to 4 times x. That's 16 is equal to 4x. And therefore, 4 is equal to x. And therefore, the answer for number 7 is 4.0 liters. So that's very simple. Now, as you can see over here, we did increase the pressure, so from 2 to 4. But in response, our volume, which is 8, it became 4 instead, hence showing the inverse relationship of Boyle's law. Very good. Next, Charles' law. I had to rip out this from the internet, so yeah. Given an oxygen tank of gas with an initial volume 280 liters and a temperature of 29.5, calculate the volume if the temperature is changed to negative 2.4. Let's do this. So first and foremost, let's convert our, what's this one? 10. So this is Charles' law. So let's copy the formula. Charles' law, V1 over T1 is equal to V2 over T2. Perfect. Now, this shows the relationship of volume and temperature, which shows that these are direct. As one goes up, the other goes up. And according to Charles' law, as the volume goes up, the temperature will also go up. First and foremost, let's convert our temperatures to Kelvin. So we got 29.5 C plus 273.15. Let's put it in the calculator. 29.5 plus 273.15. That's equal to 302.65. Meanwhile, negative 2.4 plus 273.15. Let's do that. Negative 2.4 plus 273.15. That's equal to 270.75. So, we already have the first volume, which is 280 liters, and the first temperature, which is this one. So let's name it V1. And then this one would be V2. So we are also given 280 liters. Let's substitute values. Volume 1 is 280 over V1. So that's, temperature. My bad. Temperature 1, that is 302.65. That's equal to 270.75. But we don't know what the V2 is. To solve this, we just need to cross multiply like this. I will highlight this. So that's going to be 280 times 270.75 all over this one, 302.65. That's equal, this is equal to V2. So let's put that in our calculator. 280 times 270.75 all over 302.65, and we get an approximate value of 250.49. So that's our answer, 250.49 liters. So as you could see over here, we have decreased the temperature, and in response, we also have a decreased volume. That is the Charles' law for you. Very good. So we got the Charles' law. Next one is Gay-Lussac's law. So Gay-Lussac's is number 6. So we go to number 6. Gay-Lussac's law. So, Gay-Lussac states that P1 over T1 is equal to P2 over T2. Let's write that down. P1 over T1 is equal to P2 over T2. This shows the relationship between pressure and temperature. And this shows a direct relationship. Okay, let's read the problem now. Okay, so first and foremost, we have C. We need to change that to Kelvin. So first, 30 and 800 plus 273.15 plus 273.15. That'll be equal to 303.15 if we put this into calculator. And this is 1073.15 if we put it into calculator. So this will be our temperature 1 and this will be our temperature 2. Okay, so for pressure 1, let's see. We have an initial pressure of 5 atmospheres, so we can put 5. And then at the bottom, we have T1, which we have defined as 303.15. And then this is equal to, we don't know the pressure 2, but we do know the temperature 2. That's 1073.15. And just like how we cross-multiplied with the Charles law, we're going to do the same again. So, we have the red part over here. That is 5 times 1073.15. Then all over 303.15. Let's put that into the calculator. Oh, let's just put the equals to this one, pressure 2. So, let's do 5 times 1073.15 all over 303.15. We should get a value of a very, very close amount to 17.7 atmospheres. And that's the Gay-Lussac's law, Gay-Lussac's, whatever. Next one is, I'd say for me, it's the easiest because there's no complex cross multiplying or any conversions. It's just Avogadro's law. So Avogadro's law is number 8. Avogadro's law states that V1 over N1 is equal to V2 over N2. This shows the relationship of volume and the number of moles. This is a direct relationship. So, we don't need to convert anything. We just need to read the problem. A balloon is filled with 2 moles of helium gas and 10 liters of, and has a volume of 10 liters. So we can immediately put 10 liters as our volume 1 with 2 atmospheres of pressure. Then, if 4 more moles are added to the helium gas, what will be the new temperature? So 4 more moles, that's 4 plus 2, which is equal to 6. As you can see, it's very much cross-multiply, but very simple. Don't think we need to explain this. That's 10 times 6 is 60. And that's going to be all over 2 is equal to the volume 2. Therefore, 30 equals volume 2. And therefore, the new volume of this one would be 30.0 liters. Very good. And it's now time for the final one. Ooh, I got so distracted I forgot to box. I almost forgot to box Avogadros, and I forgot to box Guy Lusox. Okay, one last. Here we go. Ideal Gas Law. Arguably the most hated one. Oh my gosh. Anyway. Ideal gas. PV equals nRT. I'll just elaborate that. Pressure, volume, number of moles, R is the gas constant, and lastly, temperature. Okay, analyze it now. A gas sample has a volume of 10 liters, so that's volume stated, so 10. With a pressure of 2.5, so pressure is also mentioned. At a temperature of 27C, but we know that 27C is equal to 27 plus 273.15 in, which is equal to 300.15 Kelvin. So that's what we put there. 300.15 Kelvin. And then yeah, we have, okay, so that's all the information we have at the first one. So first and foremost, we always know what R is. It's 0.0821. Now, we have PV equals nRT, but we want to find N. So we just do divide both sides by RT like this to cancel out this. So we get the value that N is equal to, we have PV 2.5 times 10 all over 0.0821 times 300.15. Let's put that in our calculator. 2.5 times 10 over 0.0821 times 300.15, and that's equal to roughly, did I get the same answer? I did that same answer, hold on. 2.5 times 10. Oh, yeah, I made a miscalculation on my version, but this is approximately 1.0145. So I'm just gonna leave the exact value because it's really what do you call this, specific. So we now have the N, right? We can just substitute that. We already have everything. So we put the PV equals nRT. Yeah. Yes. We got, yes. PV.
How many? 4?
Yeah. PV equals nRT. Yes. PV equals nRT. And then we are also given, let's continue. So if the temperature is raised to 327, so we need to calculate 327C. That's just equal to 600.15 K. I'm pretty sure you get the gist by now. Plus 273.15. I'm pretty sure you get the gist by now. So now we just substitute. So we just change the temperature, 600.15, times that by 0.0821 times 1.01 is equal to, we know the pressure, we know the pressure is 5, the pressure changes to 5, and then we just don't know the volume. So So let's solve that left side mess real quick. So 1.0145, I just shortened it, times 0.0821 times 600.15, that's equal to 5v. Okay, we're getting a little bit on the smaller side here. Is there anything that went wrong? Anyway, in my solution, yeah, 50. 5v is equal to about 49.986. So, yeah, that's it. The thing is, in my system, it actually detects that 10.04 is the correct answer. But according to us, 5 divide answer divided by 5 is equal to just 10. So it could be argued that it's 10, but I did put 10.04 and that worked out for me. So there's probably just a small margin of error for that one. So yeah, that really just happens in sometimes. So that's the downside of online tests than physical tests. But other than that, we're basically done with science. So if you made it this far, congratulations, you have completed all of grade 9 science. Round of applause to you. And once again, thank you so much for supporting us throughout the entire school year. We will be back for more next school year in grade 10, that's for sure. That's for absolute certainty, unless we get abducted by aliens. So once again, make sure to take care of yourselves, especially during exam week. It's coming up in 3 days. So once again, thank you so much for your continued support. 1,300 views. That's crazy. So thank you so much for listening, and I'll see you in the next study guide. Goodbye. Oh, not again. Forgot to do this. Okay, and now we're done. There we go. Thank you once again, by the way.